Hi everyone, welcome to the Math Spellbook livestream. I'm your host Peter, and basically we're going to get back into some physics problems today. So hopefully you guys are having a good Wednesday today. You made it to the middle of the week. Congratulations to you all for making it making it to this point of the week. If you guys are working and you're basically just going through a bit of a stressful week, my heart goes out to you. Anyway, thank you for joining me. If you're just basically lurking, you're more than happy to lurk and basically do whatever it is you need to do to be productive on your end. So, if it's your first time tuning in, just basically just pick up whatever it is you need to do, and just do it and you can mute me if you like, because sometimes I just talk while I study. So, but if you don't mind me yammering while I do physics problems, you're more than happy to leave me unmuted if you like. I should probably just restart the study counter actually, because I haven't gotten to the problems yet. We're still doing, it's like the second chapter, but I kind of consider it as chapter 1 of kinematic problems. So we got up to, like, I mostly do like the problems that are like around like 2 dots. So if it's 2 dots, it's like supposed to be a challenging problem, but not too hard. It's like hard, but not too easy either. So I usually do those problems. So let's see. I'm just picking out like random problems, really. Like, it's not in any specific order. This one is motion with constant acceleration. So let's try this problem. This problem looks fun. It's a pretty long one, though. Just grab my pen here. So let's just go down here. And all right, let's just highlight this. Oop. No. That's not what I wanted to do. All right, and we'll make it much more easier to see. Then we'll just there we go. I just wanted to move this. Alright, I think we did miss some things. Let's see, average acceleration, where is that? In, here we go. So we just have to write in meters per second squared. And I think next week we'll probably try to do some other problems besides kinematics. I'm just doing kinematics because, like, you know, probably do 1 week we'll do kinematics, the next week we'll probably do like circular motion or something like that. So it feels like we're actually progressing further. Because like after yesterday, I feel like we were getting a good grasp of what kinematics is. Okay, so I will start the study timer. So there we go. All right, so let's get our pen here. And I do have my calculator with me, so we are good there. Now, launch of a space shuttle. At launch, the space shuttle weighs, wow, like, so it's giving us the mass. It's giving us the 4.5 million pounds. When it is launched from rest, it takes, okay, it takes about 800 seconds to reach. Oh, we have to write some more stuff down. It to reach how much? To reach 106 kilometers per hour. And at the end of the first 1 minute, its speed is 1,610 kilometers per hour, right? Yeah, per hour. so what is the average acceleration in meters per second squared of the shuttle during the first 8 seconds? Alright, during the first 8 seconds and in between 8 seconds and the end of the first minute. B, assume the acceleration is constant during each time interval, but not necessarily the same in both time intervals. What distance does the shuttle travel during the first 8 seconds and during the interval of from 8 seconds to 1 minute? Okay, so we have like 2 time intervals we have to worry about. So let's just put this time interval 1 and time interval 2. So 1 minute. So that's technically 60 seconds, so we don't have to do a conversion factor with that. So 60 seconds. So let's just write this out so we don't get confused. So 0 to 8.00 seconds. And from 8 seconds to a minute. I'm just leaving the units for a minute there so I don't get confused. Okay. So, well, actually, let's just write the 60 seconds, the 60-second mark. That way. Okay. All right. So it launches from rest. So the initial velocity is 0 meters per second. And we're just gonna put 2 finals here. So the final velocity let's see, it takes 8 seconds for it to reach. Okay, so the final velocity 1 will be 100 kilometers per hour. So let's change that. So instead of 1 kilometer is 1,000 meters, and 1 hour is. Okay, so we shall do times 1,000. Okay, my mic is working. I just wanted to make sure. Okay, so that's around 44.7 meters per second. Okay. So, because I put like F1 here because like obviously this is going to be like the first final velocity that we deal with, but then it's going to change into another velocity. And at the end of the first minute, its speed is. So we'll put this as final velocity F2. So 1,000 kilometers per hour. So this will definitely be a lot. 1 kilometer times 1 hour. Okay. So then divide that by meters per second. Okay. All right. So I think we're supposed to figure out the acceleration, right? So what is the average acceleration in meters per second of the shuttle during the first 8 seconds, and between 8 seconds and the end of the first minute? Okay. So I think we just basically have to remember that acceleration is the difference between the velocity and the time. So we know that the difference for the first one is like 8 seconds. And 8 seconds, we basically have that. So we'll put this acceleration 1 because the acceleration is changing from... yeah, because it needs to know the acceleration, the average acceleration during the first 8 seconds. So for that, we'll just have to implant the numbers. So yeah, we know it went from 0 to... So we don't have to worry about doing 0. We just have to divide. That's all. Over 8 seconds. That is, the acceleration is 5.59 meters per second. Okay, that's acceleration 1. And then, well, not A. We'll put that. Oh yeah, it's like it's still A, but it's like this one's like I. Yeah. So now we got to do I2. And now we have to take the difference between the accelerations. Well, the velocities, I mean. The velocities. So we have to take a difference between these two. And then divide that by 60 seconds minus 8 seconds. Which results in acceleration 2. So it rose to meters per second squared. Okay, I think that makes sense. It's like in between at the end of the first minute. Yeah, from the, yeah, and we did take the time difference, and yeah. So I think that is solid. So now we're moving on to, so I think these two, we'll put that in a box. Hopefully we get this right. Assume the acceleration is constant during each time interval, but not necessarily the same in both. What distance does the shuttle travel during the first 8 seconds and during the interval of from 8 seconds to 1 minute? Okay, so since we got the acceleration, I'm guessing the formula they want us to use is basically this formula. Let me bring that up for you guys so you can see it. So we have to know the final destination at 1 and the final destination at 2. But the thing of it is that we also have to add the initial velocity to number 2 here. And not only that, we also have to remember to put the placement there. So I think the way we should write this is, let's put initial velocity, because the initial velocity in the first one is going to be 0, so we don't have to worry about that. The initial velocity in there is 0 too, so this one will definitely be like our first acceleration, and this one we'll just leave it at I2. So we'll leave that there. So it's easier for me to keep track. So this will be final velocity 1. Yeah, because after the 1 minute, basically this is, so it still has the velocity of the original one. So we'll leave that there, and so we have to put acceleration 2 here. Just put a little 1 there, so I don't know if I did. Oh, I think I did, but now it just looks a little like a smudge. So acceleration 1. So we'll do that there, and then we'll do this. Okay. Oh, forgot the little square. The little square up there. Luckily I checked. I think that's with physics, that's the good part about it, is that sometimes if you look at it just variables, it's easier to see where you've missed some things to write. So let's see. I think that's yeah, because everything is 0 on the first one, so that makes logical sense. So now we'll put the accelerations in for A1, and then the amount of time is 8 seconds. So its distance it traveled was 170.9 meters. Okay, so now this would be considered our x initial 2. So we just have to remember that. All right. So next we have to implant the other accelerations, because that acceleration changes. So this plus the original velocity, which is 44.7 times. So now we have to take the time difference between 8 seconds and so. Right, yeah, because we're putting the new acceleration in, so I think the difference is going to matter. So that time difference would be 10, and then you basically cross out the 6 and then make it 52 seconds. Yeah, 52 seconds. Okay. So the t that we're using for this one, it would be 52 seconds because a minute has to pass. And the acceleration we have is 7.74, and then we put 52 seconds squared. So the final destination. Wow, that is huge. That is huge. Well, of course it's a rocket, so okay. So I think I broke it down and everything seems to be fine. Yeah, because this velocity, because this is the final velocity after a minute, so we don't have to put that in, I think. But we do have to put the the first velocity that we got into this equation, so that way, because everything that is initial in this equation is sort of like the final from the first equation we got. So I think that is how you solve that problem. I believe. Let's just hope that I got it right. So okay, so I'm going to bring my mouse over here. Let's try. So we're doing problem number 2.29. So, oh, where are those? There it is. So I'll just drag the answers down here so that we can see them. And 2.29. Okay, hopefully we got this. Okay, we execute. Let's see. Okay, I'm starting to see familiar numbers. Okay, that's good. Yep, we got those because it says right here. Yep, 9.9. Yeah, we got that, and yep, those numbers are correct. Now, let's see. We got 79.9. Yeah, they rounded it up, but I think that's fine. They did it in scientific notation, but yeah, that's pretty close. Yeah, that's pretty close. Yeah, from 1, 2, 3, 4. How much? Yeah, 10 to the 4th power. Okay, nice. So we got it right. Yay. Yay! Nice, 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 nice. We got that right. Awesome, awesome. I'm feeling a little bit better. I'm feeling a little bit better about kinematics. Of course, like I'm not gonna say like I'm a master at it. No, of course not. But I feel like I'm getting a little bit more confident in it. Okay, that's good. That's good. Okay, let's move on to another problem. Let's move on to another problem, shall we? Let's see. Oh, here's another 2-1. I mean, at least I'm able to copy a majority of it, but there we go. Copy. I have to remember to put in some stuff in. Usually when it's numbers, they don't like input, which is very unfortunate. Okay, where's my mouse? Oh, there it is. Paste. Oop. Okay. Click my mouse. No, I just want this. No, I don't want the screen. I just want this. There we go. There we go. Okay, now I just gotta write stuff. Okay, a cat walks in a straight line, which we shall call the x-axis, with a positive direction to the right. Okay, as an observant physicist, you make measurements of this cat's motion, and construct a graph of the feline's velocity as a function of time. Oh, okay, so they actually show us the graph. The feline's velocity as a function of time. Find the cat's velocity at... yeah, they didn't copy the numbers here, so... At t equals 4.0 seconds. And at... t equals 7.0 seconds. Oops. 7.0 seconds. Let's put some space here. Make it look a little nicer. What is the acceleration? What is the acceleration of the cat at 3.0 seconds? Question mark. And at 6.0 seconds. And at t equals... forgot to put the t there. T equals 7.0 seconds. Question mark. Space. Okay, what distance does the cat move during the first 4.5 seconds from t equals 0 seconds to t equals 7.5 seconds? Do you sketch clear graphs of the cat's acceleration and position as a function of time, assuming that the cat starts at the origin? Okay, Alright. Alright, so let's draw a little kitty cat. Make it a little fun. Then we'll draw a straight line here. Put a little... oh, you can barely see the whiskers. Of course, I drew the cat very, very tiny, and little tail. We'll just put a little tail there. Anyway, the cat walks in a straight line in the positive x direction, so we don't have to worry about like changing like negatives around. As an observant physicist, you measure your measurements of the cat's motion and construct a graph of the feline's velocity as a function of time. So they already have the graph there. I wonder if I can actually copy it for you guys. So let me see if I can copy this graph. I don't think I can though. Maybe I can minimize. Let me see if I can minimize it so we can get a little bit of the textbook in here. Let me just probably drag this over a little bit like that. Then we'll just shrink it a little bit. Then we'll drag the textbook right here. Let's just see if we can shrink it a little bit. We don't need this. I think we'll just slide it over like that so we can see the graph a little bit. And I think we'll just we'll just drag the answers that we had over to this side because this is on my browser, so. Okay. Okay, so we have a graph here, and this is supposed to be graphing the velocity. So we have the graph next to us. Now, let's see. Find the velocity of the cat at 4 seconds and at 7 seconds. So 7 seconds, it looks like it goes below the graph. At 4 seconds, it looks like it like the way it looks like it goes here. If we go across, looks about like 2.5. Let's see. Yeah, it looks like it goes about to like 2.5 somewhere. Usually with graph questions like velocity at t equals 4 seconds and at 7 seconds. Because we're not given anything about its initial velocity or anything. The cat walks in a straight line. An observant physicist. Oh wait, no. So its initial velocity is 8 seconds. I mean 8 centimeters per second. So let's. So the initial velocity is 8 centimeters per second. So let's just convert that, because I don't really like. I don't like it when the units are like outside of what I'm usually used to. So yeah, we don't need to convert the time. So 8 over. There we go. We're back to meters. That's what I want. Okay. So the initial velocity is that. So after 4 seconds. So its initial velocity. Yeah, its initial velocity from the 0 point. So it was already like basically going at. Okay. Okay, good. So I'm basically getting, like, with the graph there, it allows me to actually get some more data, actually. Because usually with graph questions, like, I always feel as if, like, it's very abstract. But then again, I probably am not looking where I'm supposed to. Okay, so... we know it's 4 seconds, so... we have to find the cat's velocity at that time. So... we have initial velocity of... okay, so... we just need to find the final velocity when it's at, like, 4 seconds. So we have the initial velocity. So actually, like, let's write down the equations, because I feel like we might need them, actually. So I think we can just erase this part here. Let's just write the equations, see if they're ones we're gonna need. So, oops, that is very messy. Just put a little tail there. Half acceleration, and then final velocity. Oops, that's initial. Final velocity plus acceleration, and then final velocity squared, initial velocity squared, plus 2 acceleration. Okay. Okay, so now we have to basically figure out how fast it was going, like what's the velocity of it. So the final velocity. So we don't know the final velocity. We know the initial. We know the time, but we don't know its acceleration. So we're going to have to figure out. Yeah, because this one we don't know its acceleration. We don't know its distance either. So we can't use the third equation. We do know its initial. We do know its initial. So an initial placement. So it's at 0. The initial velocity is. I'll just rewrite it. We don't know its acceleration, so its acceleration is a question mark. We do know the time we want to use, but we don't know its final position. That's the one thing. Because right now we want to target like 4 seconds. I mean, but we do have to figure out its acceleration. We can't assume its acceleration is 0. So we are given these numbers. What else in the problem does it explain? Because we have to know where it is at 4 seconds, and we have to know where it is at 7 seconds. Or its velocity at that point, I mean. And it looks like the acceleration is constant because it's a straight line down. So that means it's going to accelerate at a constant speed. I mean, the acceleration is going to be constant. That's what I should be saying. And it looks like the graph, the acceleration is like the acceleration is decreasing. Yeah. The acceleration is decreasing, so that means it's not constant. It's gonna constantly like decrease. It's just it's like decreasing in a linear type of way. Just need a drink of water. Okay. So... Yeah, it's just we don't know the final like position, and we don't know the final velocity. If we had any of those numbers, they would help. I mean, let's think of acceleration actually, because the acceleration is supposed to be the difference between the velocity and the time. So we don't know the final velocity. I mean, this is the average acceleration. We have the time. Yeah, we had the time. Oh no, we have the initial acceleration. We do have the time too, but we have the initial acceleration. I mean, the initial velocity. Now I see why this is a double dot problem, because it's like you have to think about how to gather the information. What is the acceleration of the cat at time at 3 seconds, and at 6 seconds, and at 7 seconds? What distance does the cat move during the first 4.5 seconds from time is 0 seconds to time is 7.5 seconds? I'm trying my best not to let the problem get the best of me. Maybe there's an assumption I'm missing. So we know that the initial velocity is not 0. We know that it starts at the 0 point. So its initial position is 0. We know the time. Maybe there's something that can tell us what the final velocity is. Maybe. But I don't want to assume that the acceleration is like 1 or something, because that seems like a mathematical trick that doesn't employ anything. And we don't know the difference between the distances either. Maybe the graph will show me something, because we know we start at 8 centimeters per second on the at the 0th point. So that means the cat is already walking when it got to where we're observing it now. So it doesn't. So at 6 seconds, the cat doesn't. The cat's velocity goes to 0, which means it stops. And wait. Oh, hey Sascha. how are you? What's the best part of your day so far? Yeah, we basically did one problem and now we're doing another one. Hopefully you're doing well on your end. What am I missing? Because the velocity is 0 when it gets to 6 seconds. So that means that the cat isn't moving at all. Maybe... So if the velocity is 0, then... I mean, we could try to figure out what we get for 6 seconds. So, if the velocity is 0 and the initial velocity is meters per second, divide that. I mean, that tells us the acceleration when it's at 6 seconds. And it is a linear, it's a linear drop. So I'm thinking that the acceleration is constant, it's just that time is making it go straight down. That might be it. Because the acceleration is supposed to be negative, because it's going lower. Not much? Oh, okay. Are you taking a break from researching, or you're just basically just doing other stuff? So, from 0 to 6 seconds, so it's just 6 seconds. So the acceleration... So, divide that by 6 seconds. So the acceleration is negative 0.013 meters per second squared. Okay. So if the acceleration is constant, then that means that is probably what we should end up with. For the acceleration anyway. But then, oh yeah. Yeah, because the time is usually the thing that adds, like, puts in more. Worked on some courses I'm teaching. Oh, what are you teaching, actually? I'm actually curious on what you're teaching. Because I know you're a grad student working on your master's, right? Or was it your PhD thesis? Yeah, find the cat's velocity. So now I think we can do the... So I think now that is the acceleration we're working with. So I think we should put that in the numbers. And now I think we can do the third equation, which is... So the final velocity at 4 seconds... So that is the initial velocity plus the acceleration, which is 0.013 times time, which is 4 seconds. Oh, whoops, I forgot to put the negative sign there. Luckily I caught that. Masters? Oh, okay. Yeah, I'm actually curious on what course you're teaching. Oh. Oh yeah, because it's going down, because the acceleration is lowered. So that's the velocity at 4 seconds. Actually, I should put V at 4 seconds. That makes it much easier to handle. Yeah, I think that should be better. Okay, so now we gotta figure it out for 7 seconds. Which I think is not gonna be that much of an issue. Because we already know the initial velocity, we just have to increase the time. Times 7 seconds. Which is negative. So, actually, I want to convert this to centimeters just in case. So that way, if the answers are in centimeters per second, so it would be times 100. That means this is traveling at centimeters per second. And this one would be negative times 100. So that's negative 1 point. Okay, so the number, like, compared to the graph, it looks like they're about right. I'm teaching basic math class for people in management. I'm also a TA for 2 courses on linear algebra and another one on ODP, ODEs and PDEs. Oh, okay. Actually, I want to learn the basics of PDEs, actually, because I think, so with ODEs, I've learned up to the integrating factor, separable equations. I have to review exact solutions, I think that's what it's called, where you have, I think, like m and the derivative of I think the derivative of x plus n times the derivative of y, and I think that's supposed to be a homogeneous equation that's all equal to 0, I believe, or some other function. I have to review those, actually. Like the Bernoullis I have to review because I haven't done those in so long, actually. Okay, so those look right. They look right. Yeah, because when I look at the graph, like, actually I should move my thing here. Oh, I'm kind of covering it, so I probably should move my model. Yeah, because the way I look at it, like, this is actually close to like 2.5-ish. So I was pretty close, but of course, like, looking at the graph alone doesn't help. So, so I think we answered question A. Right. Oh, yeah, find the cat's velocity. Yeah, so we answered A. So, okay, so, wow, the first part took me like a while to think about. That's actually a pretty good problem, actually. I guess, like, this is what happens when you study physics. You have to enjoy the process. So I think we're probably going to end up... So what are we going to do? What is the acceleration of the cat at time... Okay, so we have to figure out the instantaneous velocity, acceleration. Yes, I know the clock is ticking. Yes. Okay, I guess it's break time. But, okay, I'm actually, like, I'm pretty stoked about that. I mean, like, I was pondering, like, how to get started for a while, and I was like, how do I figure this out? And the graph actually did help, because I know they wouldn't put a graph for you unless it's supposed to help you in some way. Because I do believe the acceleration is constant, because if you look at the way the graph looks like it's going down, but it's not going in a wave-like pattern, so it's like just straight down, like linearly. So I'm guessing the acceleration is constant throughout the whole entire thing. It's just that time is making it go down, because it's going down at a certain rate, which is the time ticking. I really like giving guided lectures to undergrads. I like to see motivated students. Yay. I would like to attend your course. Of course, I'm not like in the same country as you, unfortunately. Because like the thing of it is that whenever I look online, the courses, like, you can take calculus online, you can take, you know, Calc 1, Calc 2, and Calc 3, but then when you get to differential, they only go up to differential equations, and you hardly see anything. I mean, if you look hard on YouTube, you can probably find them, but you hardly see anyone teaching partial differential equations. And there are times when I feel like I want to learn, like, differential equations from, like, partial differential equations from, like, the beginning, and, like, try to work my way, like, to basically learn partial differential equations, and partial differential equations side to side. So it's like I'm learning them both at the same time, but I'm kind of learning, if I have to learn like more differential equations to get to the point where I have to be able to solve partial differential equations, like then I know where the stopping point is. But if it's like if it's like introduction and it's just basically like, oh, these are the techniques to solve a partial differential equation. But then again, you also need differential equations to finish those like solutions. But like I'm the type of person that basically is like, oh, if I can read it and I can understand it without having any context of the other material, then I basically would learn them at the same time, even though there should be like learned like consecutively. I guess that's how I am when it comes to learning sometimes. It's like, I basically like, do I need to know this? And like, if I don't know it, then I basically just go back to it. It's like, because I think for me, it's like, there are many ways you can go about it. Because I know some schools, they don't make calculus 3 multivariable calculus like a requirement for differential equations. But I think when you take differential equations after calculus 2, I mean, for me, it would probably be much more helpful because it would allow me to remember the stuff from Calc 2 much easier than, say, if I were to just take multivariable calculus like after Calc 2. Because I think with differential equations, it just feels harder because you have to remember all the stuff you did in Calc 2, which I think is kind of like monotonous because you just kind of have to remember everything. And usually for me, I can't remember everything. You know? I just like to implement the skills that I learn and just put it to use right away. But yeah, I'm just glad that you're able to like be inspired, energized by seeing students motivated. I like that. I like it when I talk about like physics with my friends sometimes, and then suddenly they get more curious and they ask me like, oh, what does that mean? And like I basically have to tell them that I don't specifically know, but at the same time it's like I just like the fact that curiosity is kind of has this way of like making people kind of like feel as if like, oh, there's more to life than just, you know, what's in front of you, you know? You know, right now I'm like trying to think about what's the next step here, because let's see, it says find, yeah, so the next part of the problem B is like, what is the cat's acceleration at t equals 3.0 seconds, at t at t 6 seconds, and at t 7.0 seconds. What's the distance the cat moves during the first? So we have to figure out the acceleration at those times. I mean, because the way the acceleration is, I think the acceleration's constant though. Right? Because like, it's going down at a straight line from the graph. Because I think the reason why it's going down is because it's going down at a certain rate, which is time. So I think we basically already answered B. Because the acceleration is the same, I believe, because it's going down in a straight line. If it was like, if the acceleration was, like changing every time, it is changing, but it's not changing at a specific, like, rate, because it's not, like, the graph doesn't look like it's, like, curvy. Let's see, usually for PDE, people start with linear equations over some nice domain, like solving Laplace heat and wave equations over rectangular. So, when you learn PDEs, when is it, I mean, do you immediately have to, like, know, like, all the stuff that you learn from, like, partial differential equations, like, at the beginning? Or do you just, like, have to learn the linear, I guess the linear first order, solutions to PDE, to ODEs, when you first learn partial differential equations? Because for me, like, if I were to study them, like, back to back, I probably would, like, study, like, differential equations to a certain point, and then when I get to partial, and then I would probably start the partial differential equations. Like, say, if it's like, oh, you first learn, like, linear partial differential equations, but you need to know all the tricks to solve, first order linear differential equations, and then, like, basically, like, I wouldn't touch, like, second order differential equations yet until, like, I learned, like, all the stuff that I need to learn for, like, partial differential equations for, like, first order linear partial differential equations. Because that's the type of strategy I'm thinking of, but I don't know if that works that way. Because, like, if it's, like, if it's first order linear partial differential equations, do you have to know all the tricks from, like, first order linear ODEs, or do you have to know all the tricks that you learned from, all the techniques that you learned from, like, ODEs in general? I think that's, like, the thing that, like, is kind of, like I think about. I would say you need to know second order linear ODE. Oh, to basically do the first unit of PDEs. So basically you have to learn up to second order linear ODEs for, like, to cover, let's say cover the first unit or the first chapter of PDEs, right? Is that what you're saying? Because I think like with partial differential equations, like, that's when you actually feel like, oh, I'm actually tackling some really awesome math there. Yeah, because those equations come from physics, and almost equations in physics are second order. Oh, okay. All right. So maybe, like, further down the line, actually, like, Sascha, I really want to ask you this, is, like, I want to learn physics, but also, like, I'm trying to learn physics, but also I want to be able to learn physics in a different way. It's like, obviously, when you learn, like, university-based physics, you have to learn, like, the algebra equations and stuff. But I'm wondering if, like, there's a way to actually incorporate, like, say, like, differential equations and partial differential equations within learning just basic university-based physics. Like, it's sort of like, yeah, you learn, like, the basic Newtonian algebra, like, well, I say algebra, it's not, like, it's the Newtonian mechanics, but through, like, an algebra / calculus lens. But is there a way I can incorporate differential equations to, like, kind of, like, enhance, like, the lesson a little bit, like, to myself? It's like I want to teach myself physics, but I also want to teach myself the hard maths that are involved with physics. If you understand what I'm saying. It's like, basically, like, it's like you're taking all the stuff from classical mechanics and, like, regular university physics, and you're just smashing them in together. And basically it's like, oh, okay, you're learning, like, the basic thing that you would probably learn in high school, but you're adding the tough part that you probably would learn, like, in, like, classical mechanics. But you're learning them at the same time, so you don't have to, like, basically it's like, oh, you learn university-based physics, and after you finish university-based physics, then you actually go into classic mechanics. Like, my idea is that I want to be able to study it so I learn them both at the same time. So it's like I'm learning them like basically as one class instead of one, if that makes any sense. Yeah, look at harmonic oscillators. Yeah, like, I have to review what harmonic oscillators are. I think, like, harmonic oscillators, like, if I'm thinking about it visually, it's like a spring that basically goes, like, back and forth, but you don't have to worry about things like friction or anything getting in the way of its, like, constant back and forth oscillation. Is that what a harmonic oscillator is? If I'm wrong, please tell me I'm wrong. Because I feel like that's why it's called a harmonic oscillator, is because it doesn't have anything interrupting its, like, periodic, like, oscillation. I hope that I explained my point clearly. And if it's completely wrong, like, please tell me. Because I barely remember things about springs, which is why I'm trying to get back into physics. Yeah, pretty much. If you want to know the evolution of such a system, you will need to solve second-order linear equations. Okay. So, like, I'm doing kinematics right now, right? What can I incorporate with this study so I can actually, like, incorporate, like, some parts of classical mechanics into it? So that way it's like, okay, now I've gotten the kinematics part of, like, say, university physics. Now I just want to incorporate the harder stuff where it's like, oh, like the first part of classical mechanics course, where it's like you actually have to use ODEs. Like, do you have a recommended type of, I guess, curricular activity I can do for that? I mean, I do have a classic mechanics book. It's just that, I still don't know, like, ODEs to actually, like, do classic mechanics yet. Because I think I've gotten to the point where it's like, with ODEs, I think I've done up to, like, first order. But I have to practice first order a little bit because I barely remember the techniques. And I don't think I've covered series solutions with ODEs yet. I mean, I think I have, but I haven't fully done problems involving them. Not to mention I have to review a partial fraction integrals. I'm very rusty with those. Yeah, basically it's like when I'm trying to learn, it's like I'm trying to learn the basics of physics, but I'm also trying to incorporate the harder parts of physics. So it's like I learn them all into like one whole lineup, where it's like classic mechanics. Okay, we've done the universities, we've done the basic, like, you know, like, I guess primary school version of classic mechanics. Now we actually move on to university level of classic mechanics, and then like you know, like, but we incorporate it with every lesson. So when we talk about, like, say, springs, we learn about the, I guess, like, the Newtonian equations, and now we actually try to incorporate the differential equations involved with harmonic oscillators. Which I don't think anybody learns physics that way. They usually learn it where it's like university-based physics, they take like 3 courses on it, and then they move on to classic mechanics, and they have to remember everything from, like, kinematics all over again. Alright, so the break time is officially over, but I will be right back, guys. Just 1 second. I know my model isn't there, but I will say when I'm back. So just give me a minute. I will just put the be right back screen on. Okay, guys, I'm back. Sorry to keep you guys waiting. Yeah, I'll just leave my model off because we still have the graph to use. So that way I'm not covering it. I didn't realize my model was covering the graph before. Okay, let's get back into studying, shall we? Alright, so I'll put the clock up and we can continue our conversation while I'm working on this problem. So I think, like, for B, the acceleration is going to be constant the whole time because it's just one straight line. So I think the acceleration for all of them is going to be what we got before. I mean, I think that's a logical conclusion to make. Yeah, because it says from Yeah, it's basically the acceleration, and the acceleration is like a one straight line. So I think if we're wrong about that, then we'll just have to learn why we were wrong about it. But based on what I see in the graph, I think that's a logical assumption we can make. What is the distance? What distance does the cat move during the first 4.5 seconds from 0 to 7.5 seconds, and then D scratch the graph. So okay, so we already have like everything we need to solve that. So for the first 4 seconds, so we can put 4.5 seconds. Let me erase that. That didn't look nice when I wrote it. Wow, that. Bring this up a little bit. Erase this. 4.5 equals. And I think now we have to put the numbers in. So we already know that the initial speed and the initial velocity, so I think we just have to put the initial velocity in, which we know, 4.5, then plus the acceleration, the half times the acceleration, which is negative 13, 0.013, and that is also 4.5 seconds squared. So the distance the cat covered was 22. We'll just put 22.8. Yeah, 22.8 meters, which is roughly. Let's times that by 100. So that's like around 22.8 centimeters. So the next part of the question, what is that? From 0 to 7.5 seconds. Okay, so let's do that. So I think it's practically the same way. Yeah, because like it's from 0 to 7.5 seconds, so I don't think you need to incorporate any differences. Yeah, because it starts from 0 and you just want to see the time from that time frame. So plus a half times 7.5. Wait, hold on. I probably forgot the negative symbol. Because it turned out positive, and it should not turn out positive. Actually. Unless I did something completely wrong. Oops. There we go. I was like, why is it positive? It shouldn't be positive. Let's just round it to 6. Oh, you typed something, Sasha. What'd you type? For physics undergrads, they usually learn about PDEs and electromagnetism. Oh, okay. For the first time. Wait, what? Don't they have to take a class on PDEs? Or they actually teach the PDEs during electromagnetism? Unless that's because I know I think when you get into regular like undergrad physics, like before a course on electromagnetism, I think they do teach you partial derivatives. I think. So are you telling me they just basically teach them like partial differential equations, what they need for electromagnetism in an actual electromagnetism course? times 100. I want to see how many centimeters it is. So the cat actually goes back a little bit. So negative centimeters. Okay. Well, the first time they see an application of PDEs. Oh, okay. In physics, they usually have a dedicated course on. Oh, yeah, that's what I thought. Because I think in PDEs, like you use practically everything you learn in that course for physics, right? Or is it only for like some stuff that you can basically don't need to know for physics? I mean, I would take like a full course in ODEs and PDEs just to get the maths, like to get to understand the math, even though it might not be applicable to all physics, like all of it, because I know there's some stuff in math that they don't use in physics. The one thing I get a little bit mixed up with is when they start, I think when they start messing around with angles. Because I know with physics and math, there's like a point where they kind of switch the theta and the phi around. Which I don't know why. Maybe there's a history behind that. Maybe you can educate me on that. Most equations in physics are PDE. Oh, okay. Gotcha. Okay, so there's more physics in PDE than ODEs. Or am I just assuming too much? Because if you were to take ODEs, right? I think like ODEs have a lot of applications everywhere, but is like PDEs like more focused towards like say engineers and like people in STEM? I mean, like, then again, there are partial differential equations in finance, too, so I probably shouldn't, like, assume that it's all going to be for physics. I mean, it could be used for physics, but at the same time, it's like, it's not really necessary for them to be just for physics. Sketch clear graphs of the cat's acceleration and position as a function of time, assuming that the cat starts from the origin. Well, I think the acceleration graph is going to be not hard, because it's just going to be one straight line. It's just going to be one plateau the whole time. Because you have all the way up to like 7 seconds, right? So like 1, 2, 3. Oh, we drew perfectly. 5, 6, 7. And since it's just going down with time, that means that the acceleration is going to be constant. ODEs are mostly used in mechanical systems. Oh, okay. So I'm guessing PDEs are mostly used for like fields or like anything involving like I don't want to say fluids, but anything that seems like it's kind of lucrative, like say like air or electrical fields, magnetic fields, like vector fields, I should probably say. I don't know if that's the right term to use. I was about to say metric and vector spaces, but I'm like, no, I'm probably jumping the gun there. Okay, for distance, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. I really don't like drawing graphs, but you know, I'm just gonna draw like as close as I can with it. So T. So I think we'll do this in centimeters, just to make it look nicer, I guess. So obviously it's gonna start at 0. It's gonna start at 0. So I'm just gonna basically do it second by second, make it a little bit easier to handle. So it starts at 0, and then basically we get 8.5 and then we'll just do 1 second. And then it's also an acceleration. It's just gonna be minimal. It's like, I don't even know if it's gonna barely get to 1. Let me just see. So we're just gonna do it all in whole integers. Actually, we should put the answer plus the initial velocity times we'll just put it right here, 0.07 right there, just so we can have a place for it, and half, oops, and then 2 squared is just 4. No point in typing that out. Well, actually, we'll just put it in meters. Just put it in meters, because I think the graph should look similar. It's just different units. Because I don't feel like converting. And do it for 3 seconds. Wait. Oh, dang, I messed up. Okay. No, because that's not right. That's not right. What am I doing? Okay. So the distance. So let's just do it at 7 seconds. So 7 seconds. Yeah, 7 seconds plus half. For mathematicians, systems of ordinary differential equations are really just the study of vector fields and their associated flow. Oh, okay. But what about PDEs? Like, what do they mostly observe for, like, mathematicians? Like, I mean, what do they, like, what exactly is the study behind PDEs? Because you said it's basically vector fields and associated flow with ODEs. Okay, so the highest we're going is like 24. Oh, nope. Why does that happen? Shouldn't be 7 times. So what about 6? What happens if it's at 6 seconds? Oh, it drops. Okay. I just want to make sure. Because, like, it's supposed to drop a little bit. That's what I was expecting it. So 6 is here. And then 7 is, like, right here. So if we do this... Luckily, I recognized what I was doing wrong, actually, with these calculations. Because I was actually, like, putting the distance, like, from the last second as the initial position. And I didn't need to do that, actually. At least I don't think I need to. So 13.4, that would be like right here. then if you do it for 8 times 3 plus... Now I see why people use Excel for this, because I'm like, I might as well just plug it into there and just do, instead of doing it by hand. But this is what I grew up doing whenever I did math. It's like you had to put everything individually, by hand. I don't think we'll be able to squeeze everything in there. Oops. 4 times a half times minus 13. Oh no, not 19. 13. And then for 4, it would be 16. And then we got up to this point. Yeah, we won't be able to fit like oh no, we are like, it's like that's 4, right? We won't be able to write 5 in there. But I'll just calculate 5 because we're already on a roll with it. That'll be 25. So that's like, yeah, so the missing piece, it's like, should be like around like here somewhere. So the graph is gonna look like this. I mean, it's pretty much like close to a straight line. Close. But it kind of curves a little bit. I mean, I kind of drew it that way, but that's on me. Okay, so I think we're done with this problem. So I don't know if we got it right. So let's, actually, let's zoom in. So it's 2.30. So let's just expand this. Do I need this? No, I don't need this. So oh, it's the next problem. Okay, we don't have to go that far. Okay, so let's just shrink this. Yeah, there we go. Okay, so let's take a look. So yeah, like the 13, yeah, because we did meters. They did centimeters. I'd rather do it meters because I mostly make it second nature to convert. Okay, so what do we got? Okay, so for B, yeah, B we got. Actually, I just want to check if that's right. Times 100. Yeah, that's correct. Okay. Let's see. So we're at C. Oh. I think I missed something. I missed something at C here. It's at 23 point... What did I write? I probably didn't check that one. I think I was too preoccupied with the negatives. Okay, so if it's like 0.8 times 7.5 times... Oops. Negative 13.7.5 squared. Oh, I guess maybe I did something with my calculator. That's why it's wrong. .4. 23.4 centimeters. But the graphs look okay. I think the reason why I was like preoccupied with this one was because like the actual graph itself, it looks like this. And it's at 7.5, so I'm like, shouldn't it go back a little bit? But then again, the acceleration is like constantly going down, so it's reducing a little bit. So I'm guessing that's because like it's still going forward a little bit, but at the same time it's like not as much. Oh, hello, Jashu 1998. Welcome. What's the best part of your day so far? Hopefully I'm pronouncing your name right. I'm reading it as Jashu or Jasu. Let's see. From the geometric perspective, PDE has a lot of applications. One of the most popular is found in special Riemann metric in and Einstein's equations, or the metric with constant scalar curvature, right? Yeah, I remember like the Riemannian metric, and they had to change it to the Ricci metric because they couldn't use the Riemannian metric because it was too big, so they had to reduce it to the Ricci metric, and then they have to also put the Ricci scalar in front of the metric tensor. I'm just amazed that I'm able to remember that. Actually, like Einstein's Einstein's field equations are like my favorite. I don't know how I memorized it, to be honest with you. Okay, so I feel like we're getting slightly better with these problems. I mean, like, I'm starting to think more in the lines of what it means to actually do kinematics. So, like, it's like my brain is developing a muscle to actually, like, get used to kinematics. I've been making figures in Python all day. Glad to be done with those. Nice. That's good. And if you guys are like basically tuning in for the first time, be sure to drop me a follow if you like. If you like math, physics, or you just want to have like a little productive stream in the background while you're doing your own work, that would be appreciated. And also, if you guys want to follow, you want to join our Discord server, let me just put it in for you guys here. If you guys would like to join our Discord server, it's sort of like our own little research, like a little research / learning space. So if you want to teach people stuff, if you want to actually like show what you're doing in your research and actually present it to us, even though we probably will not fully understand the full details of it, it would be nice to actually see what you guys are working on and actually see what you guys are actually developing within like the stuff that you hope to revolutionize the world, or at least in the academic world. And you guys can also also subscribe to my YouTube channel if you guys like probably have to like tune in for the stream for a little while, but you want to see the rest of it. These VODs are going to be up on YouTube, so you know, just something to keep in mind. Okay, so I think we can do another problem. I mean, I'm a little bit disappointed that I missed that part, but at least I got like the logic and the structures done within the other ones. So I would say that that's mainly like an arithmetic error on my part. Not to mention I didn't think too far into that. Oh, that's good. That's good. It's good that you have students that are motivated. I'm guessing you're also a graduate student, Jasu? Like, if you are a graduate student, what are you researching? If you don't mind me asking. Oh, I have to move my mouse over here. About to defend, yes. I don't understand what you mean by that. Okay, so we have another one. We have another double dot problem. Nice. They're all next to each other, which means I don't have to scroll down as much. Paste. There we go. Alright, let's see. Hopefully it got all the numbers. I don't think it got all the numbers though. Okay, a graph shown in the velocity of the motorcycle officer plotted as a time function. Find the instantaneous... Yep, it didn't copy the numbers. Like always, I have to type them in by hand. 3 seconds. Yeah, 3 seconds. And at 7 seconds. I don't know why it doesn't want to put the numbers in. Oh, thank you for the follow, Jasu. I'm working in computational chemistry. I still need to defend my PhD. Oh, nice. Hey, Fanvox fan, how are you doing? Every time when you guys drop a follow, it always makes me happy. Like, cause like the thing of it is that like being able to like do math for you guys, or like being able to create an atmosphere where you guys can do the stuff that you're doing, whether it be art or math or any type of research you're doing, or either just any type of work you're doing that you feel passionate about, or you feel like it's going to elevate you to the next stage in your life. I always feel happy that I'm able to contribute to that. Of course, you guys are doing the hard work, so like I'm not going to say like your success is mine. No, I'm basically saying like I'm glad I'm able to create an atmosphere where you can actually get your work done. Hey, Penn Center, how's it going? I will give you a shout out, Penn Center, actually. So if you guys don't know who Penn Center is, an awesome math streamer. Not to mention someone who is also teaching us awesome math wisdom on Twitch as well. So if you want to learn a little bit of real analysis or linear algebra, be sure to give him a follow. I'm pretty sure he can teach you a lot more stuff than I can. So far we've done 2 physics problems. Is it 2 or 3? I think it was 2. I think it was 2 problems, I think. Very sweet today. That made me think hard about matrices this morning. My day's alright. My day's going alright. I feel like I'm getting a little bit more... I think my confidence in kinematic problems is starting to get a little bit better. So we did this problem and we did this problem. So we did 2 problems so far. But I feel like I'm starting to develop my my kinematic brain for physics problems a little bit. Doesn't mean I'm good at physics. It just means that I feel like I'm starting to understand acceleration, velocity, and displacement a little bit better. How do you invert your matrices? Oh man, oh man. I mean, like, whenever I do a problem that seems long-winded, I don't blame people for feeling sleepy. I think, like, I did, like, a problem that involved me doing, like, several cross products, and I just felt like I was just too tired. I couldn't do another problem after that. Okay, so what is the question? Okay, the graph in figure E... Okay, so we already have the graph here. Cool. So maybe I'll probably leave this, like, from now on. I'll probably like make it like this, so that way I don't have to like scroll back to the book all the time. Let's see. Show the velocity of a motorcycle police officer plotted as a function of time. Okay, so it's a velocity graph. Okay. Meters per second. Nice. I don't have to do any conversions. Find the instantaneous acceleration at time 3, times 3 seconds, at 7 seconds, and at 11 seconds. B, how far does the police officer go in the first 5 seconds, in the first 9 seconds, and in the first 13 seconds? Okay. I missed almost you in such linear algebra streams. I hope they're going well. Yeah, I hope they're going well for as well, because I probably have to relearn linear algebra actually. Maybe I'll cover linear algebra in my streams so you guys can actually see me like do linear algebra problems. There are 2 techniques for matrices inversion that I know of. Oh, my favorite way is raising the index. Like for a matrix or for a tensor? Because I know they're not both the same way, but they kind of, like, I guess, like, in a way they can function in a way the same way. I don't know. Because, like, with indexes, like, when it comes to vectors and I guess tensors, maybe matrices, I think, is that I still don't understand like how to interpret quadravariant and covariant vector components. I mean, partially when I think about it, like when I actually like the books that I've read so far, I'm trying to think of basis vectors as sort of like whether it be covariant or quadravariant. I'm thinking of them as sort of like partial derivatives. That's I think the thought process that I developed recently, but I don't know if that's the right way to interpret it. Find the instantaneous velocity. Okay, so A. I feel like I want to make the thickness of the pen a little bit more. Okay, there we go, because it looked really scratchy. Okay, the instantaneous velocity. Okay, looking at the graph here, maybe we can zoom in a little bit, make it look nice. There we go. Alright, so we want the instantaneous, so the instantaneous velocity is the limit where, I guess the limit where the time is heading towards 3, because we want 3 seconds. No, what am I doing? Shouldn't be that. Should be, I think, distance, right? Because it's supposed to be velocity. But I think we have to look at the graph, so... I think the graph basically tells you. You don't have to do calculations much. So let's see. So from 3 seconds... So for 3 seconds, the velocity is 20, because it's just flat out 20. And for V at 7 seconds, oh, this is where I hate it the most, when it's not a specific number. But then again, hold on. I mean, it looks like it goes on 30. I mean, that's what it looks like on the graph, but I'll just write it down so I just like have it as a reference. Because then we have to do 11 seconds. Hey Jeff Gross, how's it going? You probably know this, but your chat overlay is interfering with your writing. Oh, okay. Maybe I will do it this way. Because I'm left-handed, that's why I write it this way. So maybe I'll probably do this instead. Maybe we'll just move this over here. Drag this here. Oh, no, no, no. That's not what I want to do. Let's do it this way, and then we'll stretch it like this. But thank you for telling me that. Apologies, guys, if that was also bothering you. Yeah, because I'm mostly left-handed, that's why I positioned it that way. But how you doing, Jeff Gross? What's the best part of your day so far? I was trained to use Gaussian row elimination, but just it's far it's far easier when dealing with weird square roots. Gotcha. Much better. I can't annoy you properly unless I can read what's going on the screen. That's fair. That's fair. But what's the best part of your day so far? I've been running around, but things are settled down, so this is the best part. Oh, okay, cool, cool, cool. Okay, 11. So I think 11 is going to be a little bit tougher. Yeah, because it looks like it's like in between 20 and 15. So we might have to do some fun calculations here. Probably get the acceleration. Yeah. So we might have to get the acceleration for that. So we know that 0 minus we'll go up to, I think 9 is like where it hits. Yeah, it's probably 9 here. It's barely 45. Maybe it's a 10. Yeah, maybe 10 might be easier. And it's not. It's like... Oh, wait, hold on. Oh, 10 is 35. Okay, so that makes it easier to deal with. 35 meters per second. And... I'm guessing this lands on 13. So it's like 13 minus... 13 minus 10 seconds. So yeah, because the acceleration is going to be negative, so done. Minus 3 seconds. So acceleration is like, okay. So the thing is that yeah, and the acceleration is going to be constant because it's going to go down. It's going down in a straight line, so it's going to be constant. Now I have to figure out I don't want to guess here because like I feel like the initial velocity from here is like, but then again, it's not from there. It's like the initial velocity at this point is 35, right? Yeah, then it'll be 35. So 35 plus, because we need the instantaneous acceleration. Wait, have I been doing this wrong? Oh yeah, it's the acceleration, not the velocity. What am I doing? Yeah, that's why. That's why I'm starting to get a little bit wonky. Okay, so we have the velocity. So the velocity didn't change actually. So the velocity, the instantaneous acceleration is 0 for this one. For this one, for 7. We got up to 30, and then we go from 20, so... Like, it goes from 20 to 30, so 30 minus 20, and then divide that by oh, you know what? Let's just not make it as wide. So it's gonna be 5 because we have 25. 6 is on 25. And then we have like 7, which is by 30, so it's practically 1 second. So it's an instantaneous acceleration, and it's a straight line, so it's not gonna change as it goes up. So it's about 5-ish, like 5 second. Okay, I think those are the accelerations. So. Actually, I should probably put like acceleration numbers. Those are the accelerations at those times. Do you mean 10-ish? Yeah, I'm gonna relook at it because 6 is basically 25. So 6 is basically at 25, and 7 is practically on 30. That is if I'm looking at it right. So then if you minus like 30 miles per second minus 25 meters per second, that's 5. And then like the difference between them is just 1. So it's like 1 second. You can indeed get the slope from 2 known points. Yeah. Oh, never mind. The graph is 2 seconds. The lower graph is 2 seconds. No, it's fine. It's okay. Actually, I should raise it up a little bit. I didn't realize. Ooh, I went too much. Exercises. Mistakes always happen. Mistakes always happen. So we are on 231. I think this should be it. Yeah, it's like around here. So we'll do this. Just raise it up a little bit. Oh, too much. And I'm not done with the problem. Jeez. Okay, how far does the officer go within the first 5 seconds? If you could make a slightly bigger. You just take this off. Yeah, there we go. There we go. No problem. So I'm probably gonna finish this problem and then we'll probably end stream from there. I guess we've been doing 3 problems per stream. How far does the officer go in the first 5 seconds? And the first 9 seconds, and the first 13. So I'm guessing they need you to use the accelerations as the catalyst for basically calculating the distance, or help you calculate the distance. So the first 5 seconds. So we have. So basically, the initial velocity is 20 meters per second. Oh wow, that looks really ugly. Yeah, because I also have to stream on my other channel like tonight, so I don't want to overexert for now. Quantum tunneling. Oh wow. Oh. Hello, Genzio Live. welcome. I'm just basically just finishing up a problem here. I just downloaded it from the website. I wasn't sure who was the one that told me about it. Was it you? Or was it someone else? Oh no, this is their first time chatting. Never mind. This is your first time in the chat. But welcome. What's the best part of your day so far, Genzio? And let me know if I'm mispronouncing your name. So the first 5 seconds, so we have the initial velocity, and I'm guessing the original position is 0. Yeah, because yeah, I think we can say the initial position is 0. So we have the acceleration, which is 0. So technically, we can just basically do times 5 seconds. Yeah, so let me just erase that. I don't like the way that looks. So at 5 seconds, so it's just going to be the velocity times time because it's 0. So thus, so we have 20 seconds times 5 seconds. That's around 100 meters. And then for the first 9 seconds, so 9 seconds is going to be up here. So when it gets to, actually, because it's when it's like around 5-ish, that's when it starts changing. So we already have the acceleration at 5, so we're going to need the acceleration. The initial velocity. What initial velocity should we start with? Should we go with 7? Because 7 gives us a clear number, which is 30. Or we can even start at 6, since this is on the graph. The pun was light, light as not heavy, and light microscope is the type of microscope too. Interesting. Oh, how's it going, Castle Bravo? Welcome. And if it's your first time tuning into the channel, guys, like if you like math, physics, or just need a good stream to basically get your work done, please sure to drop me a follow. I would really appreciate it. But what's the best part of your day so far, Castle Bravo test? For some reason, when I see your name, I'm thinking of the restaurant White Castle for some reason. Okay, so for 9 seconds. Huh. Now I see why this problem is a little bit tricky, because now you have to think about the changes that are taking place. Let's see. Because where was I? Oh yeah, so I think for the second part we'll just put, we can write the initial velocity as like 25 meters per second. And I think we're gonna have to take the difference between 9 seconds and 6 seconds. So I think the time difference is like 9 seconds minus 6 seconds. That's like 3 seconds. Because yeah, that's the time frame of which it changes, so we don't have to worry about too much about like adding the other original data. And then we can add the distance like to this distance. Because the initial distance... Oh wait, hold on. It's this point. That point is gonna aggravate me. Oh, hello, max time 019. I have a question. Can I ask equation card? Are you asking about a Cartesian equation? Because I see a lot of like you're French. Okay, I see. So I'm guessing I guess that English was not your first language. I don't know. I mean, you can ask. You can ask. I'll try my best to like help if I can, and if not, then there are going to be people in chat that can help you. Not really what I named myself, but rather I named myself after a nuclear test. Said my day has been nominal, nothing abnormally good or bad happened. Oh, okay, cool. Well, at least it's like a balanced day, so, you know. Yeah, the one thing that is aggravating me is this part. Like, this little dip here, because, like, it's not at 5, but at the same time, it's, like, not exactly at 6 either. Which makes it a lot harder to, like, actually calculate. But what is your question, max time? And we also have someone who is French in the chat, actually. The clear cone, aka Sascha, is French. So if you type it in French, I think they will understand and like probably relate to you in French. Most days are nominal, nothing to complain about. What are you trying to figure out? So what I'm trying to figure out is that I gotta figure out the distance that was traveled. So we're basing it off on this graph here. So I have to figure out like how far a police officer was traveling on their motorcycle during 9 seconds. Like the I think it's supposed to be the distance. Yeah, how far did the police officer traveled? So now yeah, it's just this little corner right here. That's the one thing that's like annoying me, because we still need the distance from this corner here. Because we know it changes like around here, but we don't know the exact seconds it changes. Because we know it goes from 5 seconds to... Yeah, because it's like over half, which means it's over 5 seconds. So would it be 5.5 then? But I don't want to suppose that though, because usually when I do that, I always get the answer wrong. It would be a sum of time times velocity in different regions. Like, what do you mean by that, Jasu? The area under the curve might be the other way to think of it. Right, yeah. But I don't want to do integration though, but I don't think I have to. I mean, luckily it's linear, so I don't have to worry about curves. I mean, like changing accelerations. Yeah, because I have to figure out where this exact point is. Like, I mean, in seconds. Like, which second does it stop at? If I knew that, then I can basically just write down the equation. Because I need the initial point here. Like, basically the initial point that where it starts to actually change. Right, it'd be all rectangles and triangles, right. Yeah, if I calculate, because the thing of it is that I don't know how far this rectangle goes. That's the thing. Like the length here, that's the thing that's really bothering me. Because it's not exactly at 5 seconds. It's like a little bit past it. And I don't want to estimate it to be like, say, like 5.5 or something like that. Because I know it's a little bit past 5 because the halfway mark is like... yeah, because like 5 should be like right here. And it's a little bit past it. I mean, it looks like it's close to 5.5. If I were to look at it by eye. So... then I have to basically estimate the distance. And then... that's when the changes happen. Yeah, like that's when the acceleration goes to 5 meters per second. So the time difference. Yeah, we'll probably go with 5.5, I guess, because that's the closest we're gonna get. We're probably gonna be off by a couple. So that's like 3.5 seconds, and so yeah, our original distance was 100 meters plus the initial velocity was around 20. Yeah, 20, and then times 3, so 3.5 plus half a second, and then that's 5 meters per second squared, then 3.5. So let me just actually then we'll move you over here. Then we'll do this. I mean, we might be wrong for this one, but it's gonna keep bothering me, and I'd rather just get it done like on this stream, even if I'm wrong. I I mean, hopefully we're like close to an estimate, but it's either 5.5 or 5.6. If it's 5.6, I'm gonna be like, oh man, dang it. 206 meters. Okay. Okay, so now we have to do it for 13 seconds. So now we have to figure out how far it went in 13 seconds, so... oh, you guys typed up a lot here. Let me see what I missed. You could find the equation that of that line. It seems to go through 0.625, and I think it would go would also go through 1050. You could find the equation. You could find an equation for the increasing line, and find where it intersects y at 20. And from those 2 points, you could find the equation of the line if you need to be that accurate. Yes, extending the line is a good way to get a better approximation of the slope, as pointed out. Okay. It looks like the line goes through 20 and 10 and 50. Like, you mean right here? Or you mean 20. Is that what you meant? Is that what you meant, Vemvox fam? Because, like, you also said 1050. But 10 actually has, like, is right here. Anyway, let's just continue. So we're at 13 now. So 13, it just shows it just goes to 0. So now yeah, because this is 9 seconds, so we're already at the 200 mark. So now we have to excuse me. And the velocity right now is 45. So this initial velocity is like 45. Well, 45 or 44. I think it's like 44ish because it's not touching the line. It's barely touching it. I'm just gonna say 44 just to make a guesstimate here. Because I think the reason why I'm taking so long with this problem is because I'm trying to get it exact, and I probably shouldn't focus too much on that. As long as I get it close to the ballpark, I think it should be okay. So 2 meters plus 44. And then now we have to calculate. So from 9, so we're gonna have to minus that 9 minus the, that's 4 seconds. So 4 seconds plus a half, and then negative 11.7 for, well, actually that would be 16. And if we don't get it to the exact figures, I guess I have to be satisfied with that. I have to accept my fate, whatever it is. Let's see. Oh, you type something, castle. What'd you type? The procedure would be as follows. You find the slope of the line, and we could call that the equation f of x. Then you could find x for when 20 is equal to f of x. Now, since it is f of x, the equation of the line, that calculation should not be troublesome. To find f of x, you can see what points it goes through cleanly, and 2 points. I see are 25 meters per second at 6 and go through 50 at 10. 50 meters per second at 10. Am I seeing this wrong? Let's see. 280. Oop. It's late where I live, and I'm writing gibberish to a degree. My eloquence has suffered a tad. I apologize for my poor sense. No, it's fine. It's okay. It's okay. Okay. I don't think these numbers are 100% correct, but at the same time, I feel as if we're kind of like in the ballpark with it, so we'll run with it. Alright, so 231. Let's see. The acceleration is 0. Got that. We're 7. Yeah, we were off. We were off the acceleration by a bit. Yeah. It's like around 6.3 seconds. I mean, we were close with 11 seconds. Like a negative 11.2. So we had like 11.7. So like I did my best with guesstimating stuff. That's A. Evaluate. Oh, this is B. So we execute. So they got 100 and we got 100. They got 130 and 230. 6.25 meters. So the initial velocity was 4 seconds. Yeah, so that's what they did here. This was... Yeah, we didn't get this answer really good. But that's fine. That's okay. Because I knew I wasn't going to get this problem right, because like when it comes to graphs, I really hated that I had to squint my eyes to basically find exactly where the figures were. I think this is the reason why people don't like graph questions. I mean, in math anyway. Goatee. I'm I goatee. That's well, I think that will be it for today, guys. Let me just put my model up. Okay, thank you for joining me on this. So we got 2 problems, I guess. I guess we got 2 problems. Like, one problem we kind of missed a little bit, This problem we definitely got wrong, so like I'm not too down about it, but at the same time it's like usually I know my weaknesses with graph questions, because if it's like very, very precise, especially if the graph doesn't fully display the numbers correctly. Well, I shouldn't say correctly. If it doesn't present the numbers in a way that I can read it easily, that's when I actually get a little flustered, because I have to actually like do some like calculations to actually get the exact number, and I didn't do that well. So I probably have to do more of those type of questions. I always like them. I find them easier to answer, or even if I don't know, than to guesstimate an answer. I love graph questions. Oh, that's cool. That's cool. At least you can at least you can handle them. I like, for me it's like, I guess for me it's like I just don't like the fact that I have to do extra work to basically find what a number is. And you know, like, but that happens though. That happens though. So I guess for me I just like plugging numbers in. But then again, like, I think math and physics would probably be easier if you just plug numbers in. But it did test my muscles a bit. I probably will reread this solution actually, because I feel as if it'll probably teach me a little bit more about how to actually read a graph correctly. Because I did get the acceleration, like I did get 0 acceleration right. The problem is that I got the one for 7 seconds wrong. So I probably have to look at what I did wrong there. Okay guys, I think that will be it for today's stream. So if you guys are just new to the channel and you just basically popping in for the first time, drop me a follow please, because it just motivates me to make more math streams / physics streams. In addition, it allows me to, like, you know, engage with you guys more on Discord and stuff. Thank you, Castle. Thank you for the follow. I appreciate it. Because, like, the more follows we get, the more we can basically boost the channel up. And, you know, like, if I manage to get affiliate on this channel as well, then that will make me so happy. Because that way I can just, like, continuously make more math content. So if you guys want to join our Discord server, if it's your first time on the channel, you can join our Discord server. Like, we basically talk about things from math, physics, whatever it is, like, that makes us intellectually curious, we do that. In addition, if you guys are just tuning into the VOD for the first time and you actually want to see what I did in the first couple of seconds at the beginning of the VOD, you can check out my YouTube channel. I will be uploading this VOD on YouTube. Basically, all this is just to catalog my progress. But I guess in moments like this, when you realize you got a problem wrong, it's like those moments in physics where, like, the more you do physics, the stupider you feel. So, you know, like, I know I'm not going to be a master at physics or mathematics, but at the same time, it's like I have to do better to, like, work up my skills in both subjects. Okay, so let's see if there's anyone streaming any math content or science content. Let's see if there's anyone on for today. Oh, Don Does Math is streaming. He's streaming Hollow Knight, but let's just give him a raid. So let me just open this up. I will type in the raid message for you guys so you guys can copy and paste that if you like. Raid message here. So you guys can copy and paste that if you like. And we will raid into Don Does Math's channel. So, okay, we set up the raid. And also, if you guys want to actually check out my video game channel, you can check out my Uncle Talks channel as well. Okay, guys, that will be it for today on Math Spellbook. Hello, sir. First year student at the studying economics. Please, could you answer? Oh, I was just about to do a raid. Was it more? Is it supposed to be more one? more one ho? Is that how you pronounce it? I'll just like, is it okay if I pronounce it more? how do you calculate how do you calculate 3 by 3 table determinants? I think the way you do it is that you pick one of the rows and you basically break one of the rows and columns, and then you basically break it down into like 2 by 2, like a 2 by 2 matrix. So if it's like the first row, then basically you also pick the first column, and any of the numbers that are in the second and the third, like the second and the third column, then you basically have to like do the determinants for those and multiply the numbers there. Hopefully that helps.